Hey class, we are in chapter 3, section 1, and we're talking about the atomic structure. So this whole chapter deals with where and what we believe about the atom. And so we're going to look at the history behind where the roots of the word atom comes from. We're going to look at the laws that we developed the last few hundred years to which led us to the theories that we understand today about atoms. And so when we talk about theory and laws, let's make sure we understand what's what. A theory is what people believe to be true based upon what they know. A law is what's been proven to be true over and over again. And so as we go through this chapter, you're going to see some laws, but then you're going to see some theories, and you're going to understand today a lot of what we operate on in our laboratories and what we know about the atom is based off of laws, but they're really theories. And so your generation could actually come up with a new theory of what actually is going on in the atom. So when we say the word atom, we're talking about this small particle that's made up of protons, neutrons, and electrons. And when we say the word atomic, we're just referring to things that are involved with the atom. Atomic bonding, just the way atoms bond. Atomic mass, just the mass of a singular atom. Atomic bombs, what happens when we split up that atom or bring atoms together or bring nucleuses together. So all this word atomic is just talking about the things on the level of the atom. And so this word atom actually came from about 450 BC. At one time, academia consisted of Greek philosophers who sat around and they just talked all day. They would just look at different things in the world, and then they would debate, use logic to unlock the mysteries of our world. And so there was a guy named Democritus, and I'm not sure 100% how you say his name, but we'll go with that. Him and a guy named Aristotle, who you heard before, were debating about what is matter? How is matter made? What's it made of? What's it consist of? And so here in my hand, I have a chunk of aluminum. And so it's very likely in their day, they could have saw something like this and they could have said, what is that thing made of? And in their time period, it was not appropriate for the elite, the wealthy, the educated to use their hands. And so they didn't really do experiments. Instead, they just had maybe a slave hold up a piece of metal as they talked about what it could be, and they hypothesized. And so as they look at this, Democritus, he said, you know what? I think that chunk has to be made up of an indivisible unit, some kind of particle that I'm going to call an atomos, which means indivisible, and where we get the word atom today. And that atomos is the thing that all matter is made of. It's indivisible, whatever it is, but those little things come together to form all the matter we know. Well, on the other side, you had Aristotle, and he had this opposite idea. It's kind of like he watched an episode of Alice in Wonderland, or he got caught in a Macy's dressing room and he saw two mirrors face to face. And when he saw that and when he thought about was this idea of an infinite continuum loop, that when you look into two mirrors back to back, they appear to reflect on for eternity. And so Aristotle thought that all matter was made up of something smaller, and that smaller matter was made up of something smaller. And that small particle was made up of something smaller. And that small particle was made up of something smaller. And so back in the day, they didn't have facts. They didn't have experiments. They just had the two guys arguing. And because Aristotle was more famous, more popular, his idea won out. And so for the next 2,000 years, the sciences of humanity of humans really didn't care to look into the idea of the atom. And we really kind of ignored it and just thought all things were made up of something smaller infinitely. And it wasn't until about the 1700s that this idea of the atom came back around. But now today you can see that an atom for us is the smallest particle of an element that retains its chemical identity. So again, what we're saying is in this chunk of my hand, I have a block of aluminum. So it's an element. But all throughout this are a bunch of atoms of aluminum. There are these things that have 13 protons that stick together, that clump up to form our block of aluminum. But the atom there is that smallest piece that gives aluminum its chemical properties. That makes it shiny, makes it lustrous, and makes it solid and hard at room temperature. So the other difference is when we think about chemical reactivity is maybe think of the difference between a hydrogen atom and a helium atom. A hydrogen atom will have one proton. A helium atom will have two protons. A hydrogen atom will typically have one electron or no electrons. A helium atom will typically have two electrons. Now, because of the way they're made of their protons, neutrons, electrons, they react very different in different situations. And think back in history. The Hindenburg blimp. It exploded because somebody did not pay attention in their sophomore chemistry class and put hydrogen in this blimp that was reactive, that exploded, that caught tons of people on fire and people died. Opposed to if they would have used helium, if they would have filled it with helium atoms, the helium is stable, it's inert, it's a noble gas, its outer shell is full of valence electrons, which we will talk about later. And since it was stable, it would not have blown up, and that's what our blimps today are filled of. They're probably filled up with some kind of mixture, but basically helium would work. And so now as we look on, we can see, again, this guy Aristotle and Democritus, they disagreed. And in their slave-based culture, they didn't work with their hands. They did not perform experiments. And so Aristotle did not win because he had better facts or better proof. He won because he was a better arguer, and he was more famous. And because of that, we really didn't pay attention to the idea of atoms until about the 1700s. Well, in the 1700s, chemists started to believe that there was something in elements that it could be broken down to, but not necessarily by ordinary means. And so they started to realize that there is some kind of indivisible unit in our elements, and that this indivisible unit, which we will come to know as an atom, could form together with other indivisible units to form compounds. And we were able to discover this through the advancement in our balances, through the way that we did our experiments, the way that we began to organize our data, and build upon the laws that other scientists have learned through the years. And so because of that, we were able to, in the last few hundred years, come up with 3 laws that dictate how we think about the atom today. So the theories we operate today come back to these 3 laws. And those laws are the conservation of mass, and the law of definite proportions, and the law of multiple proportions. So let's think about the law of conservation of mass. This is very similar to the law in thermodynamics that says energy is never created nor destroyed. Well, in chemistry, we say mass is never created nor destroyed. So basically what that means is no human has ever created anything. Take a desk, and you might say, well, someone created that desk. No, that's incorrect. No human truly created a desk. All they did was take the wood and change its shape, took the metal and transformed it, and put together some other atoms to make the plastic, to mold it. And so they already took what was around them and created the desk. So in our world, the law of conservation of mass and the law of conservation of energy says that we cannot make mass, and we cannot destroy mass, and we cannot make energy or destroy energy. So everything we have was already here before us. The energy we have comes from the sun, or the energy we have is already locked up inside the matter in our world. And all we simply do as chemists and scientists is manipulate, rearrange, transform that mass or that energy. And so when they begin to realize this, they believe there had to be something that existed that was never created nor destroyed, but just manipulated or transformed. And at the same time, we begin to come up with the idea of the law of definite proportions. So let me say one more thing about the law of conservation of mass. One thing that I think humans could maybe get credit for someday is the one thing they can create, and my class's guest is today, is maybe the miracle of life. My wife is pregnant. We're about to have a kid here in about a month. And so I've been told it's a miracle, but that's probably the one true thing, that spark of life that humans create. The physical aspect of it, the body, we know that comes from nutrients and the DNA and all the way it's built up. But that spark of life might be the only thing humans have ever actually truly created. Everything else was already here. We're just modifying it. So as we discovered this in the last couple hundred years, that helps us to get to the theories we have today. One of the other laws that we have today that gets us to where we're at in our understanding is the law of definite proportions. Definite proportions. All that means is that when we study different compounds around the world, if we study the same compound, it has the same chemical makeup no matter where it comes from. So take, for example, salt. If I went and got salt from the Salt Lake City, or if I went and got salt from the Mediterranean Sea, and if I ran an analysis on it, I would find it has the same ratio or the same percentage by mass of sodium to chlorine. And so what this means is that sodium chloride, salt, exists in a 1-to-1 ratio because of their mass, because it takes 1 chlorine to make 1 sodium, that they exist in a 1-to-1 ratio. The other law is like it, and it's called the law of multiple proportions. And it's just simply saying that carbon monoxide and carbon dioxide can both exist. Carbon can have a 1-to-1 ratio existent, or it can have a 1-to-2 ratio. But these laws help us lead to the theories that we'll talk about tomorrow.